In this next example problem, we're going to be dealing with an infinite sheet of charge. So when we're dealing with sheets, we're going to put it in what I refer to a Gaussian pillbox or a Gaussian rectangular prism. And one tricky part about this is that you can imagine the sheet going through this styrofoam thing that's supposed to represent the Gaussian surface around the sheet of charge. And you have to keep in mind the sheet has a top and a bottom to it. Even though it doesn't really have a height to it, it still has a top and a bottom to it. So we have to deal with the electric field coming out of this side and the electric field coming out of this side. So it becomes 2 times the length times width because you have to deal with both the bottom and the top of the sheet of charge. Alright, so we have an insulated large square sheet. We're given the dimensions 150 centimeters by 150 centimeters since it's a square, and it has a net charge of 75 nanocoulombs. And we want to know what the electric field strength at 100 micrometers is and the electric field strength at 200 meters. And the difference between A and B is going to be a difference in perspective. When you're right up against the surface of the sheet of charge, it's going to look like it's infinite, so we can treat it like an infinite sheet of charge, versus when it's very, very far away, it's going to appear like a point charge. So we're going to see here a little bit of where the charge distribution leads to a different electric field strength based upon your distance from the distribution of charge. Alright, so as I showed in the preemptive video, we're going to put our infinite sheet of charge inside of what I call a Gaussian pillbox, because that's what the textbook I learned in called it. You can also think of it like a rectangular prism or a box. So we're going to start here with Gauss's law. We always want to start these problems with Gauss's law, because remember we need to start with something from the equation sheet. And once again, we're not worried about electric flux. So our electric field is what we're looking for. Our area here is going to be 2 times the top or the bottom of the box, so 2 times length times width. And then Q enclosed divided by epsilon naught. So I've rearranged this to solve for the electric field. I plugged in the charge, which was given in problem 75 nanocoulombs, or 75 × 10⁻⁹ coulombs, divided by 2 times the area, and area would be 150 centimeters by 150 centimeters. Convert that into meters. I encourage you to convert to meters before you square it, and then times the electric constant. So that gives me an electric field strength of 1.88 times 10 to the 3 newtons per coulomb. In part B, since I said it was going to look like a point charge, I've written down the point charge equation, plugged in the coulomb constant of 9 times 10 to the 9, the charge 75 times 10 to the -9 coulombs divided by the distance. So the R in this case is distance, so that's the 200 meters up here, and that gives me an electric field strength of 0.0169 newtons per coulomb. So it doesn't matter how the charge is distributed in these problems. So when you're very, very close to this sheet of charge, it looks like it's infinite, so you would use the relationship for infinite. When it's very, very far away, it's going to appear like a point charge, so you use the point charge equation. And don't worry, I'm not going to give you anything that's somewhere in the middle where you're seeing that sort of change over between making it look like an infinite sheet to a point charge. We're just going to deal with extremes in this particular course.